Hi everyone, I'm Kirsten from Idera, and I'd like to welcome you to today's Geek Sync titled Designing Data-Intensive Cloud-Native Applications. This webcast will be recorded, so you will be able to view it again if you'd like, and the recording will be available in our Resource Center on aquafold.com in a few days. The presentation slides will also be available on our community site after the session. I will paste the link to the forum in the chat feature. We will have some time for Q&A, so if you have any questions, please feel free to ask them in the question feature in the GoToWebinar control panel, and we will get to them at the end of the presentation. We are very excited to have Samir Behara, System Architect with EBSCO Industries, here to discuss the high-level design principles that will help you build scalable, resilient, and maintainable systems in the cloud. With that, Samir, over to you.
Thanks, Christian. Well, good morning, good afternoon, everyone. And this is Samir Behara. I'm really excited to be presenting at the Idera Geek Sync today. And let me just go ahead and get my slides up. Okay, so a little bit introduction about myself. I'm Samir. I build software solutions using cutting edge technologies. Have been working on the cloud platform for the last 2-3 years. So this presentation is kind of details about my experience moving applications from on-prem to cloud and a lot of the architectural patterns which has helped me in this journey. So I'm a frequent speaker at technical conferences. I'm a Microsoft MVP in the data platform, and also the author of .NET-Vibes.com. So most of the content which I'll be covering in the next 1 hour, you will see detailed blog post, detailed articles in my website. So today is my birthday. So I was pretty excited that the Geek Sync is on the same day. We had the World Cup of India versus New Zealand today. I don't know how many people follow cricket World Cup, but India lost, so that was a bummer. But we will get started with this presentation, right? So, okay, so what are we going to cover in this session today? So I'll start with monolithic applications on-prem. This will be a journey from monolith application. We'll go towards how to break those monolith into smaller components, go towards microservices based architecture. We'll also discuss about few of the cloud migration strategies, some of the cloud native architectural patterns, a lot of architectural design patterns which can help you in this journey of cloud native. Also, I'll touch base about serverless databases, which are getting very popular with a lot of this cloud native space. So starting with a monolithic architecture. So for the purpose of this demo, I'll be kind of talking about a order management service, wherein a user talks to this order management service, which has a monolithic database associated to it. So what can go wrong with this architecture, right? So I've worked with multiple applications early on in my career, which had this kind of architecture. And there are kind of multiple issues with such architectures. The first one being the code base is huge, right? We have added a lot of technical depth on the application side, on the database side, and the code is tightly coupled. So it's very difficult if you want to kind of scale those applications based on the new business requirement which you might be having. And again, if you have multiple teams working on such one monolithic component, you will be having longer development cycle, right? Because there'll be a lot of changes coming in. You need to do a lot of coordination between teams, and then you need to have a big bang release once a month or 3 weeks or once a quarter. So that kind of is one of the biggest challenges with such monolithic applications. And you also have to have a fixed technology stack, right? Here on the code side, you cannot bring in different technologies because you have all your code in one language, maybe .NET, C#, Java, Python. right? And from the database side as well, you might be having relational, which has been very popular over the years, right? And one more issue is the performance. So the larger the code base, the larger the database, you might be bumping into a lot of performance issues because your database might grow in size. So how do you keep up with the performance? So these are a few of the issues with monolithic applications. And this kind of can be one of the reasons why you want to break down such architectures into smaller components, right? So the first thing which you can do when you want to break down this kind of big monolithic application is following domain-driven design and having like bounded context. So you need to design your application based on domains, which aligns with the functionality of the application. So it's like following code first approach over database first approach, right? So you design your models first. So this is kind of fundamentally a different approach than the traditional mindset of first designing the database tables when starting to work on new requirements or greenfield project. So here you identify your domains, your bounded context, and then just try to identify your smaller components. So what this gives you is once you identify the bounded context, you have pricing as one, currency as the other, and the ordering as the third bounded context here. So based on the business requirement, business use case, you can then associate a particular data store technology as well. You're no more bound to have relational. You can have a combination of relational, non-relational technologies as well. So taking one step ahead, I've seen a lot of architectures which has the components, multiple components talking to a monolithic shared database. So here we have broken down the order management service into multiple components, right? So we have order service, title service, currency service, pricing service, and all of them talking to a monolithic shared database. This as well tells us one thing, that in this journey from monolith to microservices, it's kind of the most difficult part is to break down the monolithic database. So it's kind of easy maybe to break down the code level, but breaking down the database requires a bigger effort. However, like having this centralized database, such an architecture has its own issues as well. So what can go wrong here? So tight coupling is one thing here. So the traditional design of having this monolithic database for multiple services, it generally creates a tight coupling and inability to deploy your service changes independently, right? So if there are multiple services, as we see here, multiple services accessing the same database, so any schema changes which say team A makes on the order service, it needs to be coordinated with the other teams as well, right? And in real world, this can cause additional work and it can delay your deployment cycles as well. Another problem is difficult to scalability, right? So it's difficult to scale individual services with this design, since you have the option to scale out the entire monolithic database or not. Improving application performance as well becomes a challenge, right? So with a single shared database, over a period of time, you can end up having huge tables. The number of rows might get huge. So this makes data retrieval difficult, since you have to join multiple big size tables to fetch the required data. So that can be one issue as well. Thinking through more, I would say, like most of the times you have a relational store generally as the monolithic database. This constraint all your services to use a relational database. However, there will be scenarios where a NoSQL data store might be a better fit for your services. And hence you don't want that tight coupling to be there. So this can be, these 3 or 4 reasons can be few of the issues with having such a architecture with centralized database. So you need to break that monolithic shared database, right? So once you start doing it, one of the key principles which we should keep in mind is databases are kind of private to each microservice. So in this diagram, we have order service and the pricing service. So one thing which we should keep in mind is no microservice can directly modify data stored inside another microservice, right? So in this diagram, the order service should not update directly the pricing service database. So it should only access it via the microservice API. So this helps you to achieve kind of a consistency in your microservices architecture, or else very soon once you have multiple components talking to each other, you will lose that integrity of data. So finally, I would say once you start breaking your application down into smaller components, again, this might take you a long period of time depending upon the complexity of your application. But this is kind of the desired state, right, wherein user talks to different components, right? You have order service, which has its own data store. So order service owns its own domain data, and it can interact with that. So you have title service, currency service, pricing service. All of them have their own data store. So this will allow you to deploy individual services independently. If you have multiple teams, they can own each of these components and they can deploy independently of each other. So that's kind of the biggest benefit which you get from a microservices architecture. Scalability as well. Like if you look at a real world scenario, an order service will have different scalability requirements than a currency service. But now there is no more restriction. You can scale your order service as per the traffic it receives, as per the business requirements. So that's again one of the bigger benefits, and you get the high cohesion, loose coupling between the different components, right? So you know that your applications, your services are now aligned to your business domains. So all in all, you can do multiple releases a day, and you can get rid of most of the disadvantages of having a monolithic application. So this is kind of a journey from monolithic application to service oriented to microservices. So we start with a monolithic legacy application which talks to a database. Then you take one step, go towards service oriented architecture. I would say we have a shared database, and then kind of gradually start breaking down your primary data store into independent databases and get into a ideal microservices journey, microservices architecture. So one very critical piece of the microservices is you need to have an automated CI/CD pipeline for each of your components, right? So you have broken down the monolithic application into multiple components, but you need to have different CI/CD pipelines for each of those components so that you can independently deploy those changes, right? So here in this diagram, what I've shown is, okay, a user comes in, developer, he checks in code to GitHub, triggers a CI build using Azure DevOps or Jenkins as well. And then you have the pipeline. So in the pipeline, you can have a number of stages for verifying the code changes which you have checked in. What's the state of that, right? So you can have a stage for unit testing. You can use different libraries. The front-end code can have their own unit test. Your database code can have its own unit test using TSQL or database projects as well. From a quality perspective, SonarQube, which is very popular, so you can use any of the static code analysis tools to look at what is the technical depth which is associated with your application. For deployment, you can use Docker containers. As part of the pipeline, you can also do some load test, performance test. There are a lot of open source tools which you can use there. And for security scans as well, if you want to have that as part of a pipeline, you can use some of the tools. So these are kind of primarily a few of the critical stages in the pipeline if you want to automate your deployments. So a little bit about cloud native architecture, just trying to put it in a picture, and it's basically I would see it as a combination of all these good patterns. It starts with having smaller components which are you can deploy independently, like microservices. You have containers. You are following DevOps principles and having CI/CD in place. So kind of it's the combination, I would say, of all these architectural patterns itself. So coming to some cloud migration strategies. So moving to cloud gives you a number of benefits, like faster time to market. You can scale your services as required. However, there is always a debate about what is a good approach when it comes to, say, cloud migration strategies, right? So I would say that there is this kind of no secret mantra for success here. So most of the time it depends upon the application which you're trying to migrate. So you need to ask a number of questions here. So are we trying to migrate a monolithic application? How much technical depth is associated with the service? What is the current state of the service, right? And is there a need for refactoring the service for improving performance or not? And sometimes selecting these applications which needs to be migrated to the cloud, this also involves a business decision. So uh, you need to check that, okay, does the application which you're planning to migrate, does it have a high enough business value so that you can justify its movement to cloud and allow additional efforts for refactoring that application, right? So if your current on-prem application is generating revenue but is suffering from performance issues and your customers are kind of raising concerns, then it does make sense to tackle such kind of scenarios. So from a cloud migration strategy, I would say, like, you have two areas which you can, two different direction you can go with. One is kind of a lift and shift approach, so where you move your existing applications to the cloud as is, like with minimal code changes. So this approach is faster, but then there are some disadvantages as well, wherein you cannot leverage the true potential of the cloud, since the monolithic application has a lot of technical depth accrued with it. So you won't get the immediate benefit. And moving your application from on-prem to cloud as is kind of indicates that all the associated technical depth which you had accrued over the years, you are as well carrying that to the cloud, right? So another approach which you can take is modernizing, so which involves kind of re-architecturing your existing on-prem application before moving it to the cloud. So if your existing monolithic application, it cannot scale to meet the increased business demand, then maybe re-architecturing the system and moving to the cloud seems to be the best solution. So there are a lot of advantages with this approach as well. So this will allow you to build the system in a way to take advantage of the cloud native services and functionality. So in a longer run, it's kind of the optimal approach, right? And you are re-architecturing the existing application, keeping in mind the best practices, the best guidance from an architectural pattern. You know what are the problems with the monolithic application, so you don't want to repeat those, and you're breaking down the components into smaller components. So that's kind of the best part. The disadvantage, I would say, is it takes time, right? Whenever you think of re-architecturing your solutions before moving to cloud, it will be time consuming. You need to spend some more efforts as well. So this is kind of one of the guidance which is on the cloud migration. They call it as 6 R's. And so as you see, we have the cost and effort in one of the axes, and the time to migrate. So the first one, retired. When you start looking at your monolithic application, you try to see, okay, does it make sense to move this component to the cloud? Is it required? Is it even being used? So if you see a few components which are not being used, they're just sitting idle, so you just retire them, right? Again, you start doing some more analysis, and you try to look at the profitability, you look at your business gains, and you then figure out that, okay, to move this application to the cloud, I might take 2 years of time, and this is a huge effort, and the business might not agree. So in some scenarios, we can just retain that unless there is an issue actually with your application. So the rehosting is another option, which is kind of the lift and shift approach. Replatforming is lift and shift with some amount of refactoring. So the core application architecture, it remains the same, but you might leverage kind of some of the benefits of cloud by using some managed instances like databases and all. Repurchasing is mostly moving to a different SaaS product, which is there. And refactoring, as I said, is kind of making changes to your application, to the core logic, breaking it down, and making sure that it is cloud compliant, right? So as you see from this diagram, the refactoring, the cost and effort is more, the time to migrate is more, but generally you get, once that is done, you get immediately the benefits of being in a cloud environment. So talk about polyglot persistence. So most of the applications I built earlier in my development career were monolithic relational data stores. We had limited choices back then compared to what we have in current days with the evolution of microservices and cloud native technologies, right? So relational and non-relational data stores, they have their own use cases. So the relational databases, I would say they have rigid schemas, and data is stored in a structured manner. And you can enforce data integrity rules by using foreign key constraints and all, right? And data consistency is kind of the prime importance there. Whereas in non-relational, there is no concept of, relationship, and you can store it in a denormalized format. And with polyglot persistence, you're just enabling the development teams in your organization to understand the business use case of the applications and have kind of flexibility in choosing the appropriate database technologies for developing the microservices. And as you see here in this diagram, we have a number of data storage technologies here. We have relational, wherein you can store data having a predefined schema supporting the ACID kind of transactions. And you have time series data, which is databases where if you want to have some more insight into the data which changes over a period of time, you can use time series database. I think Prometheus is kind of the leader in this domain. Document database is very popular. It stores kind of data in a flexible schema, and you can define new columns on the fly. And you can store it as JSON documents, and each document is kind of assigned a unique key for the purpose of fast data retrieval. So there are a lot of use cases to this document databases as well. Key value is kind of non-relational databases that stores as key value pairs. Kind of if you want to have super fast performance, so you can use these key value pairs. Graph database, kind of optimized for storing and navigating relationship between a highly interconnected relational data set. That's kind of one of the use cases of graph. Search databases as well, optimized for providing millisecond latency for all your search solutions from the user interface. In-memory databases, I would say for providing very fast output, you can use caching to avoid redundant calls to the databases, right? So that is kind of one of the benefits. So as you see, there are a lot of options, and based on the business use case, you have the flexibility of choosing your own database technology once you're in a kind of microservices cloud native space. So it all boils down to selecting kind of the right database technology for the workload. So while finalizing the data storage technologies, you need to have a good understanding of business requirement, and you can take an informed decision amidst a number of available database technology. And each of these database technologies, they have their own strengths and weakness. So probably ask a few questions like, okay, what's the use case from business perspective? Is it a read heavy or a write heavy workload? What's the number of reads and writes? How many concurrent users needs to be supported? is horizontal scalability required for the use case? How much data you are trying to store? What is the data growth? So based on a lot of these questions, you can figure out what's the right database model which you can go with. One of the interesting, I would say, architectural pattern or guidance is CAP theorem, which says that, okay, a distributed system, it cannot simultaneously be consistent, available, and partition tolerant. So a distributed system can only have like two out of these three guarantees. Like when we say consistency, it's like you have multiple data nodes and all of them returns the same data, which is the most accurate current data, right? So that's kind of consistency. From an availability standpoint, I would say a node will return a reasonable response within a particular amount of time, and there should be no error or timeout. And partition tolerance says that, okay, the system continues to operate despite some of the messages which are failing, some of the network issue. So it's kind of very difficult for any of the database technologies to have all three of them. So you can always select two of them and go with the option. And as well, there is something called as eventual consistency. Now, like with eventual consistency, systems are kind of not designed to be identical in real time, but it can take time to be consistent at some point once all the required processing has completed. So it's like eventual consistency is kind of key if you want to develop some loosely coupled systems which have high scalability requirements. Say like in a banking use case, right, you might want to have strong consistency, strong consistent data, so that your account balance is same when queried from your laptop, from your mobile. So that won't be a good use case of having eventual consistency. But there are some other scenarios where you can actually suffer, like you can allow your data to be updated after some delay, and there you can have availability. If you have more availability requirement than consistency, those use cases will be a good fit. So let's talk about few of the scaling requirements, right? So with traditional web application development in an on-prem environment, there's generally a large number of associated constraints. You have infrastructure provisioning, you have limited access to the ops team, you need support from the ops team. Scaling, if you want to scale based on a traffic spike, it might be difficult. And continuous maintenance of infrastructure is as well required. And kind of your development effort is dependent upon your upon the infrastructure procurement, about the availability of the hardware, right? And that can delay a few of your delivery of your business features and kind of functionality. So in a cloud environment, you have a lot of flexibility, I would say, once it comes to scaling. So you can benefit from the capabilities while designing some of the data intensive application, wherein you can scale your workload dynamically based on fluctuating workload which you receive. So vertical scaling is kind of when you allocate additional resources like CPU or memory, and it will give you immediate performance benefit, right? Once you scale out your database. But you can bump into scenarios where your database cannot handle sometimes the spike. So just scaling your database vertically, having a larger instance size gives you that performance benefit. But generally, if you have the spiky kind of workload, you might bump into scenarios where you over provision your resources, right, with vertical scaling. Like if you have load coming in the beginning of every month and it slows down rest of the month, if you just have a larger instance throughout the month, you're basically not making good use of your resources. But with top cloud providers, with Azure, with AWS, Google, right, the process of scaling up and down is very simple, and you can change your database instance on the fly. So that's what vertical scaling. Horizontal scaling is interesting. So if you want to handle kind of more user request or process kind of an increased workload, which is beyond the capabilities of a single database instance, you can leverage the benefit of scaling out your database instances by implementing horizontal scaling. And there are a number of ways in which you can scale your databases horizontally. So you can add more read replicas as well. You can introduce a caching layer. You can say an in-memory database wherein you reduce the number of database calls. That can be a way to horizontally scale as well. And then you can partition, you can shard your database into multiple servers to provide, to improve the read and write performance. So one way to, if you want to improve your read heavy workload, if you are having kind of a read heavy workload scenario, you can use read replicas in the cloud. So what you do is from the application side, it is easy because you can spin up multiple instances of your application in the cloud by using some auto scaling policies. But from the database side as well, you can create multiple read replicas, and read replica is nothing but just a copy of the database instance, right? And all the read workload can be handled by the read replica. So that way, if your application is kind of read heavy, all the reads, you can have multiple threads running and they can read from the read replica. So that's kind of one of the ways in which you can handle this read heavy workloads. So from a availability perspective as well, you don't want you want to avoid failure scenarios for your applications. You want to avoid downtime, so it's kind of recommended to have your deployments or your applications, your databases being hosted in multiple availability zones just for high availability. So in this diagram we see that the primary instance is there in one AZ, and you have the replica which is in a different availability zone. So in case the primary goes down, the replica can immediately become the primary, and it can ensure that your application is kind of having the high availability. Now for read replicas as well, you can have multi-AZ deployments. As you see here, I have 3 availability zones, and I am making sure that the read replicas, they are kind of different availability zones, and it gives me a lot of confidence on the application that, okay, that the uptime of my application is really high, right? So there are like, okay, how much downtime you can have. So you have 99.99, 0.999. So it's like there are different metrics there, different calculation as to how much downtime this application can have. So this, by having multi-AZ deployments, it's a good way of improving your application availability. So database sharding is kind of a potential solution to a problem scenario where you want to scale out even the write transactions to your database, right? We talked about read heavy workloads, but what about write heavy? If you have such a scenario, so you can have sharding, and sharding can be just defined as partitioning of data across multiple servers to just meet the high scalability requirement of modern day distributed systems, I would say. So as you see in this diagram, we have 5 different shards. And so basically, instead of having all the customer information in one node, we now have 5 different shards. So the customer A to D is in one shard, E to Z is in another, K to N, O to S, T to Z is in the other one. So we can have kind of such a sharding mechanism as well. But one of the problems with such kind of sharding is it kind of creates sometimes an imbalance, right? You might have a lot of customers starting with A to D, then K to N. So you will have kind of imbalance between shards. So one of the key principle which you should keep in mind while sharding is generally try to maintain balance. So in that case, you can use something called as some hashing strategy. So as you see here, I have a hashing strategy. You can use any algorithm for your hashing, and then you can distribute the data uniformly across multiple shards. As we have here, we have 3 shards, and we are just using a hash strategy to distribute the data equivalent. We talked about caching. So caching is kind of another way in which if you want to improve database performance. So if you have, once you break down your monolithic application into say 5-10 different components, so what will happen is to cater to one request, now instead of hitting the monolithic application and getting a response back, that request is going through multiple services. So service A talks to B, talks to C, talks to D, right? So if you want to improve your database performance, if a user comes in, makes the same request, you don't want to do the calculation all the time, right? So you can introduce a caching layer. So what in the diagram here, you have the order service, which instead of talking directly to the database, we introduce a caching layer. So first of all, we check, okay, is the data in cache? If yes, we read it from the cache. If it is not there, we fetch it from the database, we save it in the cache, and then we read it. So this kind of gives you very high read performance if once you have caching implemented. And as well, sometimes you want to avoid that round trip to the database. So in a microservices architecture, in a cloud native space, so you want to, the caching works great. It reduces the load on the databases, and all your operations, the read operations are faster. So as I was talking about, we have now broken down one component into multiple components here, right? So sometimes after you start breaking it down, this is kind of the state which you will end up, wherein you have one service talking to service A, talking to B, talking to C, talking to a middle service which owns the data store. So what can go wrong here? What happens if the second database goes down? So basically you have cascading failures on all these 4 services which are kind of depending upon that data store, right? And which you want to avoid. So what happens if this third database goes down? So you'll have a lot of other, in this case, a lot of more services actually are depending upon this database, so which might go down. So you want to avoid having cascading failures in a microservices kind of architecture, right? But no matter how well you design your architecture, failures are bound to happen. So you need to follow some of the architectural patterns to kind of save your day. So one such architectural pattern is circuit breaker design pattern. So what it does is, say your database service C, the database is down. So instead of continuing to send requests to that service C, what you do is you create a fallback mechanism. You know that the database is down. So if you keep on sending requests, those are going to fail, and you need to give time for the database to recover. So you kind of give a fallback implementation. Fallback implementation can be different based on your business and the application itself. You can give an error message back, you can give a default value back, or you can give a computed value or something back to the client, right? And you give time to the database to recover. And once it is the database recovers, you can send messages and you can process them. Having kind of a queue, a transactional queue as well, is beneficial because it ensures that you're not losing any messages. So kind of if you want to design resilient, fault tolerant microservices, you need to have circuit breaker in place. Event-driven architecture is kind of another common pattern to maintain data consistency across different services. So what it does is, as you see here, order service gets a call, gets a request, it calls pricing service, it then calls currency service, it does the calculation, passes it back to pricing service, and then to order service. So you're going through each by each to each of the dependent services. So instead of waiting for an AC transaction to complete processing and taking up system resources, what you can do is you can make your application more available and performant by offloading the messages to a queue. In the second diagram, we have introduced an order queue between order service and pricing service. So whenever a request comes in, it gets, we post a message to the queue, and immediately order service is available to the end customers to take in more requests. And we know that we have given it loose coupling here with the queues, but it's not, there is an eventual consistency model here, right? So we take a request, we push a message in the queue. Pricing service is kind of listening to that queue. It picks up that message, processes it, gives it to the currency service. So eventually that record is processed. But this is a way in which we can make our systems more available to the customers. Same way, designing for scalability, you have an application which talks to an order service, which talks to a database. So if you want to scale the service out, what you can do is you can introduce a queue, and you can have an auto scaling policy defined. Say if you get more than 1 million messages in the queue, you can, instead of having one instance of the order service, you can auto scale it to like have 4 instances, and then the processing can take place. So you can design it that way as well. So just a little bit about serverless architecture, since it's getting very popular in the cloud native space. So earlier we used to have the data centers, we moved to VMs, then to containers. We are still taking care of all the infrastructure behind the scenes. So serverless comes in, wherein, so it does, so the word serverless, it doesn't mean that there are no servers. So it just says that you just have offloaded that responsibility, the infrastructure responsibility, to a third party. Right. So we'll just talk about serverless databases a little bit, because there are a lot of use cases where serverless databases can be a great fit. So we talked about this over provisioning of databases with vertical scaling, right? So there, I think serverless databases are great, because you just pay for for the usage, right? If the database is not getting used, you are basically scaling that down. So it can automatically start, scale on usage, and shut down when it's not being used. So some of the use cases which I think I have seen beneficial is, if for the test databases, when you're starting up with your development effort, so it's generally, if you have a serverless instance, it's a good one, because say you complete your development at 5 o'clock, leave for the day, and come back next morning to continue with your work. During that time frame, your database can automatically shut down, and no cost will incur in the cloud. And again, if you have some variable workloads, so if you have some spiky kind of workload, say you get frequent, like you get a heavy workload on the day 1 of every month, and then the rest of the days it's kind of less. So having serverless, it can automatically scale out based on the spike, and once the traffic decreases, it can again scale back in. Also for new database development, so if you're doing a new greenfield development, you don't know what can be the ideal instance size of your database. So there you can start with a serverless, and then once you have more idea about what traffic that application is supposed to handle, you can at that point convert it into a provisioned database as well. It's kind of cost effective once you start having hundreds of database in the cloud. Every penny matters, right? So you can it saves cost after hours as well. So suppose like for every service which you have, you might be having different environments. You might have a development environment, a staging environment, and then the production environment. So the development environment, those databases can be serverless, because there might be a period of time where you are not doing any active development on a service. So having serverless there makes sense, because you know that when there is no active development, the database is just scaling in and you're not incurring the cost. So like serverless database, if you see this is kind of a screenshot from say one of the database instance over the last 2 weeks. You see some spikes here. So these are the times when there are requests to that particular database. So you see the spikes, but rest of the time, the capacity unit, as you see, it's all flat. It's at 0 CUs here, which says that, okay, the database has scaled in and you're not incurring any additional cost. So this is kind of how serverless databases work. A lot of good use case, but you need to be careful as well, because you should not, if you have some workloads where you have continuous load throughout the week, those might not be a good use case of serverless. So pretty much what I covered here, these are a few of the use cases which I have seen can be used for serverless. But if you are trying to go there, just evaluate your use cases and take a gradual step there. So, okay, so I think we are on time here. And thank you so much. And I wanted to cover kind of, this was a journey for me. And a lot of this content which I covered, I've been working on it over last couple of years now. So it's a long journey. I try to compress a lot of this architectural patterns, guidance, guidelines, architectural stuff into 45 minutes. But any questions which you all have, if you can post it in the chat, I'd be happy to answer. Or else my Twitter handle is Samir Behara, and you can always reach out to me there on my website and .NETvibes.com. As I said, a lot of these content which I covered, I have detailed blog post there. So Kirsten,
Wonderful.
I think I'm on
Thank you.
time. I completed
Yes.
on 45 minutes.
Thank you,
Over to
Samir.
you.
We appreciate your presentation. Now we're going to head over to Devin Gallagher, who is the Idera Senior Sales Engineer, for a demo of Aqua Data Studio. Devin, over to you.
Okay. Thanks, Kirsten. Thanks, Samir. Very interesting presentation. Always learn something new on Idera Geek Syncs. So tied with today's presentation, would like to introduce those of you that may not be familiar with Aqua Data Studio, or for those of you that have heard of Aqua Data Studio, the latest version is up to version 20. And so I'm sharing my environment now, but just starting with the Idera homepage. Here's the GeekSync page that you can revisit these presentations. But now you'll start to see Aqua Data Studio here on the homepage. So from the products link, you'll see Aqua Data Studio. Here's a posting on the main homepage as well. And then in the background, you can see the product open. And so just under Help About, you have links to the product homepage. And then we just wanted to introduce a few of those resources from www.aquafold.com. And so Aqua Data Studio joined Idera in 2017. And so they've been aboard for a number of years. And there've been 4 major releases under Idera. So we've had version 19.0, 19.5, version 20. And Aqua Data Studio continues to add new databases. And so in terms of some of the environments that Samir was talking about, and the on-premise or cloud, there's over 30 different platforms supported by Aqua Data Studio. You can see a range of environments I'm connected to in my navigation tree on the list on the left, and we can go through that list in a moment. But then here are some other areas that highlight those. So if I click on the resources page, you have a platforms link here. And so sometimes this is a starting point just to show the scope of where Aqua Data Studio can connect and then provide different types of users the ability to get their job done, right? So from developers to DBAs, analysts that need to access data and perhaps build visual analytics or move data and tell a story with their data. This is the type of tool that can help those types of users. And I'm sure many of you are familiar with database IDE productivity tools. So you have lots of resources here from the Idera page or to the aquafold.com page. And then let's start by just diving in and looking at a few areas. There's a combination of pop-out or dockable windows, and then floating or standalone windows. And so here you can see a navigation tree on the left, some different SQL editors or code editors, and then a file navigator on the right. Then there's also a combination of standalone windows or floating windows, right? So you have the visual analytics as a standalone window, you have the entity relationship diagram as a standalone window, and then also the visual query builder. But just to start with the very first icon in the connection window, server, register server, let me expand this window and just show the scope of environments that Aqua Data Studio can connect to. So this list continues to grow. This product started over 15 years ago with traditional RDBMS platforms, and now you can see the addition of the cloud-hosted environments, the Google environments, the Amazon environments, and look for that to continue with the RDS platforms being added in the 20.5 release later this year. This list is alphabetical, and as you highlight a connection, you can see what information is needed to connect to that environment. And so there's been a lot of development into this area to save you time and lets you connect very easily. So there's bundled JDBC drivers, and then as you select a different connection, you can see what information is needed. So here's an Amazon Redshift example. Here, if I switch to, say, a Google BigQuery environment, you can see how the connection information will vary per platform. Here's SQL Azure, SQL Server has some different options, Oracle has some different options. And then as you mouse over these, you'll see some different connection information. So notice here and say, as I hover over the Postgres, I see /Aurora Google Postgres. So look for the RDS platforms to be added in the 20.5 later this year. And really just starting here to show that the continued development and platform additions. Snowflake was recently added, as well as Embarcadero Interbase, and those environments now are available with all the benefits of Aqua Data Studio. So you have the navigation tree here that would have some familiar areas. If I was just working on SQL, of course, you have the ability to execute or generate DDL, easily execute one or multiple scripts. And then as we were tying this to Samir's presentation when he was mentioning some of the refactoring that needs to go on as you move from one environment to another, of course, Aqua Data Studio would be a very strong IDE to help with those type of testing and moving code from one environment to another. If I explore the navigation tree, here you can see a Snowflake environment that I was navigating into. Here in Amazon, you can see different groupings. So you'll have the familiar database management security, or perhaps schema drill down, and then depending on what platform, you can see some of the differences in the architecture as you navigate these different environments. Right click within a connection, and here you'll see different abilities in terms of creating objects. So here, if I was to just drill into, say, a cloud environment and then start right clicking on creating objects, or perhaps if I stick to a more local environment, right click here and you'll see your create, alter, or drop for objects from databases to tables, indexes. And then here, as a bit of a time saver, under the tools menu, I had opened up the schema script generator, server script generator for an example in, say, Snowflake. And so here you can see perhaps the differences in terms of the object support that continues to be added for, in this example, a data warehouse like Snowflake. Look for the RDBMS platforms to be added next. And then easy to use productivity areas, right? So the visual query builder lets me drag and drop tables to build SQL graphically. Here I have some different examples that might be easy to see at the same time here. So if I was dragging and dropping tables in a SQL Server environment or a Snowflake environment, I can have Aqua Data Studio write that code for me, perhaps save me time or hand this off to users that need to then work with the data. So you have time-saving abilities with the visual query builder. And then for those users that need to work on data and move data and work on data visual analytics, for those of you familiar with, say, the Tableau or Power BI type functionality, this is a very popular area for those type of users, data-focused users, and that's included in Aqua Data Studio versions without any additional licenses. So you have the visual query builder, the visual analytics, and then perhaps a little more DBA-centric, you have administration features. So you have monitoring capabilities, scripting capabilities, and then even lightweight table relationship diagramming. So for those of you that need to perhaps reverse engineer an environment that you've inherited, or as Samir was mentioning, moving, rehosting, replatforming, Aqua Data Studio is the type of tool that can help with easy ER scripting, and then the ability to even compare ER scripts from different platforms, and then of course generate or migrate table indexes, related objects, not enterprise modeling, but for lightweight table relationship diagramming. Aqua Data Studio is very strong at those areas and continues to add new platforms. Okay, so let's close out by revisiting the product page. Again, it's www.aquafold.com. That's the company that came aboard Idera, and so we've kept that user community and the branding and name recognition of this now nearly 18-year product. And then you have the Aqua Data Studio homepage, which has had some enhancements added. If you've perhaps visited Aqua Data Studio in the past, lots of new resources here for you to visit. Perhaps to help you in terms of decision making, where you have white papers from customers, lots of training videos and content, and then of course you have the Idera GeekSync page that this is now tied to as well. Okay, let me pause there and hand it back over to Kirsten. Thank you everybody for joining, and we look forward to joining future GeekSyncs.
Thank you, Devin. It looks like we do have time for a couple questions, and we had a few come into the chat feature. So question for Samir, what about a situation when you need the same data available to multiple services? So for example, a product list is needed by both pricing and order services.
That's a good question. So it's like, so first of all, that particular data store which you have, it needs to be owned by, say, the product database. It needs to be owned by the product service itself. And now we have the customer service, which as well wants information from the product database, right? So that's the question. So in that cases, what you can do is the customer service should not fire a select star from the product database directly. If it needs to get some data, it has to make an API call to the product service, and then let product service fetch the data from the database and hand it over to the customer service. That way you are just maintaining the integrity of your database. And there might be some other scenarios as well, where you might have like, so one database, you have broken it down into 5 different data stores now. But if you want to cater to one request, you need to make 5 different database calls and aggregate those, right? So there you can see that it might become a problem. So in those scenarios, what you can do is you can have another common data store at the top, which is kind of your decentralized data store like Elasticsearch or something, wherein once your database, a product database is updated or your customer database is updated, it triggers a message and to the centralized database and updates that data store, and all your API calls are actually hitting that centralized database and not the individual middle data store. So that's kind of one way in which you can make sure your API calls, whatever comes from the front end, they are having like millisecond latency, and you don't have to combine, aggregate all different data from your different data stores all the time. So again, I'll be happy to discuss more on this kind of architecture if you hit me up in my Twitter. I can walk you through a few of the scenarios which we have as well, and where we have exactly tackled this problem. Great question again.
Perfect. Thank you, Samir. It looks like we're out of time for today. I will pass along any questions that we have outstanding to Samir, so he
Sure.
might be able to answer some of those for y'all as well. I'd like to
Absolutely.
thank Samir for an informative presentation and Devin for a wonderful demo today. I invite you all to head over to aquafold.com to download a free trial of Aquadata Studio, which Devin highlighted for us today. This webcast has been recorded, and we will send a follow-up email to all attendees with a link to our resource center, where the recording will be available for viewing in a few days. The slides from today are also available on the Idera community at the link provided in the chat. I hope everyone has a fantastic week, and we hope to see you back at our next Geek Sync. Thank you.
Thank you so much, everyone.